Well, I will start the presentation. Okay. Can you hear me? Listen. Okay. Let's start. I will introduce about the quantum Fourier transform and the okay. And start. So the content is introducing GFT quantum Fourier transformation and transform and start with look about the Fourier transform. The Fourier transform is defined by the equations on the slide, and it has this is used for the changing the variables from the position to wave wave vector in physics, and or it is used for the frequencies and the time variable. So it is used for the solving differential equations or signal analysis or many fields. Or sorry for my bad English, but okay, so I will introduce about the QFT, since it is the quantum version of the discrete Fourier transform in signal analysis, and this is important since many of the algorithms are using this QFT. So examples, for example, Shor's algorithm in the figure uses inverse QFT gates in the last part, and the quantum-based estimation algorithm and the algorithms for hidden subgroup problem are using QFT. So let's take a look about the DFT. The DFT definition is given on the formula, and this is has a similar form of the inverse DFT is on the figure. I will the slide. Since we cannot take continuous variables from the computer, so we have to sampling some points, and DFT is needed to use. So in quantum computing, DFT is just called as classical Fourier transform or just Fourier transform in this field. Since I I introduced the DFT first, since QFT has similar form with the DFT, which is defined on the formula, but in this equation, let we denote omega n the exponential 2 pi I over n so jk and 2 pi I over n the omega n, then we have the very similar form with this equation. So first inverse version is has similar form, only the sign is changed, sign is flipped, and yes, the similarity is on this formula. Sorry, enumerating formulas, formula, and that. So in these equations, then we can ask about why we use QFT. There is no difference between the equations, but then I will introduce it soon. So wait a minute. Let's just look about the QFT. Our in matrix representation, to look a QFT more easy. And you can see the matrix form. So the here, yeah. 이제 너무 다 써놔서 then we have to implement it with as in the quantum circuit. So that we want to reduce the time complexity exponentially. So take a variable, so exponentially reduce the time complexity. So start with the look at the basis transform. Simplify our problem. We can denote the n cube system with so n cubic system has 2 squared n and 2 to the n basis it has. So we can represent it as binary numbers with n digits. So I will denote it q0 to qn minus 1, and then we can denote the cat q be the cat q0 q1 blah blah qn minus 1, and the q be the number in the formula, and we can sorry, so I must be revised as k. Each qk is 0 or 1, so that it is binary, and we take a QFT in this on the q, cat q, then q becomes the formula. these situations becomes children and just in the sorry. I just continue the presentation. So n, capital N is defined as 2 to the small n, and the QFT is taken as the first formula, and then J KQ becomes Kronecker delta JQ. So the summation about the J log of only without the Q term. So we can put it in the formula, and I expanded it with binary form, and then the next equation. The first line is same with the last equations, the last slide, and we can expand K in the exponential term to product of each exponential K to the term, and we can we can vector out it as a tensor product form, and you can check the expansion directly to check this vectoring is right. So the problem check the problem implementing quantum circuit to QFT becomes the changing the basis from the original binary basis to this binary this basis. So example, the state example. Yeah. If we had four qubits and the basis was 0, 1, 1, 1, then it looks like the first figure, and we can if we if this transform, that in the basis becomes the figure, and the labeling, number labeling 0, 1, 2, 3 is reversed in my basis, and just look it reversed, and we can see that in the last equation, the Q, the first term in the tensor product is exponential high IQ, which has the values only plus 1 or minus 1, and but the last term has all points in the Z2 to the n minus 1 are 2 to the n points in the complex plane, and unicircle, and we can see that in the second figure, qubit 0 has is our qubit theory. base 몇이죠 이거? 8분의 7 over 8 pi 7 pi over 8 base and the cubic theory in the figure which we labeled as cubic zero has base pi in the last one. And so since for the implementation we have to reverse the basis ordering to make a circuit well so and it is well operated since the tensor product is just can change its just the order is just you can think that position changing so I reverse the each term just as like in the formula and so if we define the capital N as a 2 squared n 2 to the n and the we square it and each term has small n so you can equally divide the square root and the vectors are all well normalized and you can denote it as a cat q0 prime q1 prime to the q n minus 1 prime and then we only need to check the base change. The first basis change is just well working since the second q1 prime or and q n minus 1 prime can be implemented only just shifting the q just in the implementation. So just look about the first digit, first cubic, and you know that the expansion is like this in this equation, and the sigma, the summation term about the q is please read the text. If we had q0 if we have qj digit, if it is 1, then we have to rotate the phase by pi I qj over q to the j minus 1 I to j, and if it is 0, then we don't have to change the phase. So we need to use the control gates in this algorithm. So we define two gates. C rotate is controlled rotate gate, and U rotate gate is just a mutual rotate gate. And it works if we check Q if we check the Q is 0, then just 0 takes they just works as identity matrix, but the QJ term is 1, then it works as a U rotate gate, which gives phase shifting on the cat one. So we can implement the computer circuit like this figure. The dots in each vertical gate, in each European gate, is connected with another qubit that is check the qubit which we want to check. It is 1 or 0, and so this changes the basis spread. And second and third or MF1, it has the similar form, since it works since in like J2 to the Jn, it is labeled as J1 to the Jn in this figure, and the substitute is 0 to the n-1. Then first cat is only need the which has period 2 to the n-1. So the last term, so the first term Q0 does not affect to the its base, so we only need the left terms. So the implementation works better. So the QFT works like this, and the conclusion, QFT is a quantum algorithm based on the EFT, and the time complexity is reduced as n squared, and this was are there any? This is the further reading. The first paper is explaining the QFT first, and the second paper improved the QFT method. And are there any questions?
What is the quantum property of this QFT method? Like, what is the speed up?
Since we any qubit system has 2 to the n basis states, so it has number of freedom. And is exponential.
What's the n level from n?
Large n.
Large n.
Yes. So in this circuit, we have n squared, small n squared gates, and each has time complexity 1, and so the QFT's time complexity becomes so you ask. I denoted this large n, not the big explaining this, and this denotes the small n, not yeah. This is just data set, size of data set, and in this complexity. While I use the n as the to the n, so here is not. Just size of the data set. 네. 그냥 앞에서는 이 n제곱계 한국어로 다시 설명을 하면 그냥 앞에서는 이 n제곱계만큼 그냥 그 라지 n, 캐피탈 n을 그냥 그렇게 정의를 했었는데 지금은 스몰 n으로 얘를 잡으면 그냥 데이트 개수만큼만 그냥 명을 주니까 이거 그러니까 만약에 앞에서의 라지 n을 썼다면 앞에 식과 뒤에 식의 차이가 그 앞에 건 n 로그 n이 되고 뒤에 거는 로그의 n의 제곱꼴이 돼요. 그냥. are there any questions?
Thank you for your presentation. And just wondering, what is the treatment?
Okay.
So anyone who can do it,
Sure, algorithm.
then maybe basic explanation. I was just wondering what that.
그러니까 앞에서 설명했던 표 알고리즘이랑 수정이랑 또 다른 알고리즘이 있는가? I think the PFT may be used in the as a part of another algorithm, so maybe it does not be importantly work when the algorithm is explained. So does maybe the Shor's algorithm or estimation algorithm is depends on the PFT highly, but yeah, I'm not. 한국어로 모르겠어요. 그러니까 PFT가 중요하게 작용하는 알고리즘들이 앞에서 설명했던 알고리즘인 거고, 네, 약간 부차적으로만 쓸 수 있는 알고리즘들 같은 경우는 약간 소개가 안 돼 있는 것 같아서 저도 열심히 찾아봤는데 넣지를 못했습니다. I searched about the where is the PFT used for the another algorithms not introduced in my introduction, but I couldn't see in my level. Yeah. Is it? No questions in Zoom?
There's no.
There's no questions anymore, then I will close.
Sorry, but one last question. Who is that?
PFT. Good. 4%.
Security is well known and very famous algorithm. I actually don't care about who invented it. Yeah. I got curious.
And 4% invented it.
Well, that's the actual paper, not the
Yeah.
first paper.
The first paper, 1994. And there is more about the PFT, not only this algorithm, but the approximation. since this paper is not only 다루다 그러니까 트래픽만 다루는 건 아니었던 것 같아요. 더 뭐가 많은데
저 내용 중에 트랙티가
네, 초장에 있어요. 그거 보고 영상 그랬던 것 같아요.
제목부터 왠지
이거 올리겠습니다.
발색을
네.
그래서 more have any more questions?